First, thanks to Joseph and Franklin for the invitation, and an extra thanks to Joseph for all the details of behind the scenes, the details of organizing everything. I know it's a lot of work. Thanks to everybody for sticking around late on a Sunday as well. I'm going to talk about what the title says. What got me there, we've seen a few talks already yesterday and today that mentioned contractive IFS fractals and some other things along the way that have some of the same flavor. This will as well. So I put together a talk that's sort of formative. It takes us through the build of the related stuff. Perhaps there's a few mildly intelligent things I did along the way in that. But that's not the way that I came to this problem. So I thought on the first slide I should mention why I even thought of thinking about this. Oh, and I should say this is a joint work with Bryce and Boreland, who was a master's student who just finished and worked on this with me. So there's a paper from 2015 in Fractals, StarShaped Sets Inversion Fractals, very similar to the title of the talk. There is very little mathematics, and it's all about pictures, and the pictures are gorgeous, and you go, wow. And then you read the description of why things work, and the graphs are drawn using the chaos game, which is a typical thing we use to draw these things, but a tweak of the chaos game. And between these ingredients, you're like, well, why is this working? How's this working? And so I started looking for the paper trail, and it goes back to these other two papers. You see, one is manuscript and preparation. It never finished the preparation stage. So the other two papers talk about the circle version of this process, and so the 2015 paper is the extension to something more general, which we'll talk about shortly, so I'll define all these things in a sec. But when you go back to the 2000 paper, they also have pretty pictures, and there's no explanation of the mathematics. They say the math appears, then you go back to the 95 paper, and they say the math will appear in this 96 paper, which never existed. So as far as I can tell by pretty rigorous survey of things, these details are not in any paper. I should say that the circle inversion related stuff exists broadly in the geometry literature, and was of interest to all kinds of guys. Apollonius and Mandelbrot even has stuff in the book that you referenced, right, on Nature. Anyway, let's go to the definition and build slowly and see if I don't bore you too much. So let C be a solid circle. It has a center O, a radius R, and we'll call the boundary die C. First point, for useful purposes, will represent any point in R2 in terms of the circle. So the center will be sort of the base point. We'll take the radial ray, swing it around 2 pi, and I purposely have this, the red button. I purposely have this scaling factor on the radius so that I can tell if I'm inside or outside the circle. W is just the usual unit polar vector, and R then scales it to be radial length, and then the A bigger than 1 tells me I'm outside the circle, A equals 1 I'm on the circle, the boundary, and less than 1 I'm inside the circle. So this will be convenient for figuring out what we're doing. We'll also see, and not necessarily needed for the circle case, we'll see the notation pi of x to be the projection of a point x onto the boundary of the circle. If x is the origin, I don't know how to project, but all the other points, it's the projection along the radial ray onto the boundary. Picture is straightforward. I'll try and go ambidextrous here. So the center is O, I didn't label it for some strange reason. Angle T, we shoot the radial ray out. There's the point X, it's O plus ART. This is the case where A is bigger than 1. If I project them onto this boundary point, circle C, radius R. Straightforward, right? Okay, so if C is such a circle, great. For a point X that's not the center, I can draw the radial ray from the center to X, and then I can define the circle inversion map. The circle inversion map is a point on the radial ray so that it'll be a point on the radial ray, and the thing that follows, let me show it, then I won't, I'm going to explain this first and then come back to this. It's the point on the radial ray whose scaling factor is 1 over the original points. So that's the inversion part, right? So if you're 2r out, the inversion point is a half r inside. This is the way to write it in terms of the projection onto the boundary, which in this case, of course, is just the radius r. So this is a nice way to write the definition. In the papers, they will all write this as the definition of t of x, but of course the points that satisfy this are the circle inside the original circle or outside of all the points that are the appropriate radius away from the origin, and we want the one that is on the same radial ray, which is typically not mentioned in the papers. We see that the inversion map takes the boundary to the boundary, cool. The interior goes to the exterior, and the exterior goes to the interior, cool. Everybody's happy. Here's a picture. So if I start at the same sort of point as before, and I don't know why I wrote A1. If I write AR for this, then the inverted point is 1 over AR on the same ray. And when you multiply, of course, it's R squared. Everybody's happy, right? So the nice result, and it's very easy to prove, is that if you apply t to 2 points x1 and x2 anywhere, except neither is the origin, and again, this should just be O, I'm sorry. The relationship you get is that the distance between the points, the original distance, gets scaled by a 1 over A1, A2, where A1 and A2 are the radial scaling vectors, or factors, sorry, for x1 and x2 respectively. Proof is very straightforward if you build this notation. Just plug in and figure out what this animal is. He's that. And if I put in tx1 and tx2, I get the exact same expression, except the radial scaling factors will all get inverted. And then sure enough, if you peel off a 1 over, I'm doing the square here, if you peel off a 1 over A1 squared, A2 squared, and put it out in front, you get that guy because these two terms can be swapped to be those two terms. Very pretty. It's sort of elegant and pretty and simple all at the same time. So from there, imagine now instead of just one map, we build a system of maps. So now we're moving towards the IFS kind of sensibilities, right? So let Ci be a circle, I equals 1 to n, centers OI, radius is Ri greater than 0. Any point x in R2 can now be represented with respect to any of the circles. So we start dropping i's on everything, which is why I had the A1 earlier, because it was lifted from a different spot in my prep. Associated to Ci, every circle has an inversion map associated to it, so we just drop some i's inside. Everybody's happy, right? Now, based on the previous stuff, if the circles are pairwise non-touching, so they're all isolated from each other, then if I take points inside Cj and I apply Ti to it, it takes these exterior points to the interior of Ci, the factor in front of when you write down the relationship between the distance of the image of the points and the distance of the points originally, 1 over A1, A2. A1 and A2 are both bigger than 1, so this is a contraction. Cool, with respect to V2, right? And there's proof in one line when you can do the details. So, define X to be the union of all the circles. And now I want to build a setup where a single map is contractive on X, right? Which is what we do in the IFS world as well.
Are these circles still mutually distinct?
They're still mutually distinct for now. They won't be in a little while, but they are for now to make it easy. Yes. So I said formative on purpose, right? So now I want to define, because the T's, Ti is expansive if I pick points inside Ci, I define a new map that is Ti if I'm outside, but it's just the identity if I'm inside. So T bar I contracts the D2 distance between points when at least one of them is outside. This is a theorem. If they're both inside, it doesn't do anything. Okay? Better yet, and here comes the beautiful spot, if I take the pairwise union of two distinct guys, Ti and Tj, that's a contraction, and it sends everything into Ci. Okay? So in IFS world, this is playing the role of the FIs or the WIs or whatever letter you like to use for your contractive IFS maps, right? So for X and X, let's define T to be the union of all of the pairwise distinct compositions, Ti and Tj, Ij from 1 to n. Everybody's happy, right? T from X to X is contractive. It builds from the previous. So all the usual IFS machinery can kick in now. I've got a contractive family of maps on a complete metric space. I can introduce the set valued version of the maps that works on the complex subsets of X and produce the property that there's a unique set attractor. Again, nobody's touching, to go to Andrew's point, right? I can plot approximations of this by using the chaos game. And to do this, so this is the first thing that was in some of the papers. They say, let's play the chaos game, and I'll do this by selecting individual single maps, T1, T2, T whatever, for the different inversions. And the explanation was all the maps are contractive. Well, the way that things are set up, if you don't redefine the maps, they're not contractive if you're working on a point inside your own circle, right? So, but with our setup, because of the bar, if you are in the circle and you pick the T for that circle, nothing happens, right? So that map is just redundant. When they played the chaos game, they would discard that map because they were worried about the expansion that it produced. We don't have to discard it, we keep it. If we take the pairwise, we should be selecting pairwise compositions, but if I build a string of individually selected guys, I can just view that as pairwise selections, and if by bad luck I pick T1 composed with T1, the second T1's irrelevant because it's the identity as far as the points are concerned. Make sense? I hope so. So now we can adjust for overlaps. This is a horrible expression maybe, but all I'm saying is n is the maximum number of circle overlaps. So the circles are laid out, and I see that there's a point x that's inside 5 circles. 5 is the biggest value for any of the points, the maximum number of circles any point is in. That's what n is. M must be less than n, so that there is no complete overlap at any point of all the circles. And with that proviso, I could redefine the previous setup to let this, the T bar be the composition of m plus 1 maps, because I can get to m plus 1. It might be all n of them. In the previous example, there were no overlaps, so the maximum number of points, circles a point was in was 1. That's why we composed 2 maps. With this construction, you get access to the contractivity of one of the maps eventually, right? When you compose, it's quite pretty. Okay, so pictures. Oops, click the right button. Pictures. My pictures are not as sexy as everybody else's because I didn't have time to make the pixels smaller and run a bunch of stuff, so I apologize if they're a little clunky, but they are colorful. So these are the inversion points. They're the centers of the circles. My circles are overlapping, and then I just played the chaos game a whole bunch and plotted the slightly bigger dots than pixels because I knew I didn't have time to build a lot of stuff. Similarly here. Cool. Some extra ones. They're very pretty. The structure is nice. I've done nothing with dimension, nothing with any of the other things yet. It's just, I was just curious for justifying the framework. So circles, not touching. Overlapping circles, everything's okay. Now we move to the 2015 paper, this extension to StarShaped Sets. A StarShaped set is a straightforward object. It's a closed object, continuous boundary. There's a point inside that if I stand at it and point my arm and turn around, I pierce the boundary at only one point all the time, all the way around. That's a StarShaped set. There might be many points like this. So for example, the circle, every point inside, if I stand at it and spin around, I hit the boundary at one point. So every point is an element of the kernel, which is the collection of all the points that have this property. In a proper star, in this case, the interior pentagon is the kernel of points that have this property. These guys that sort of fold in strange ways or have holes in them are not star-shaped. Okay? So, what changes? Let's try and follow the same roadmap and see what happens. So sticking with n equals 2, I should say there are some other papers I didn't list that draw beautiful pictures for sphere inversions, and they're quite pretty, but the same ideas here extend. Sticking with n equal 2, so StarShaped set, I can represent it this way, and notice the only difference now is as I spin around, the radius changes. Cool. The inversion map is exactly the same with the projection onto the boundary, but the projection onto the boundary is now the variable radius, right, depending on what angle I'm at. Everybody's okay. We continue. This was the key argument of the previous case. I put in magenta T1s and T2s. In magenta, yes. And you see what happens, right? In the previous argument, when we factor out the 1 over A1, A2 squared, the A2 hits an R of, oh, I put T2, T2. That was stupid of me, right? So let's do this more carefully than I've done it. When I pull out the A1 squared, A2 squared, I get A2 squared R of T1, A1 R of T2. I don't know why I didn't change that one. That's very dumb. Okay, so this only equals, like the 2 and the 1 interchange, right? The 1 and the 2, they're in battle with each other. If the radii are different, I don't have the ability to say, hey, that's the same as this. This only works if these two things are equal, which was true for the circle when I'm standing at the center. Even if I work with circles and take a step away from the center, now the radius changes and this line is broken. So the same proof doesn't work. Direct extension fails because this is not true in general. So what do? Well, is it true? So I went to this setup. This is an ellipse. You have to look at the axes difference, right? It looks almost circular maybe. This is an ellipse. That's the point that I'm going to invert at, the kernel point. Every point is a kernel point. These are 2 points starting outside. If I zoom in on it, they have the same y value, but the distance between them is 0.05. When I do the inversion into the circle, you can see that they're sort of, I don't know, co-radial or something, right, along this radius. When I invert them in and zoom in and check, the distance doubles. So it's expansive with respect to the Euclidean metric, okay? So it's not that I need a different argument for D2, it doesn't work for D2, okay? So let's fix things. To fix things, I'm going to embed the projection inside a new metric. The projection isn't defined at the origin. So all I'm doing here is saying, let's redefine the projection. If this is a point outside the circle, the projection would be to cross out the A, right? Make A1, which is what I've done up here. But if I'm at the origin, I want this to have meaning, so I arbitrarily decide to pick angle 0. It doesn't really matter what I pick, just so that it has a value. So that when I come into here, I have a metric, a new metric that I'm defining, ds, on all of R2, including the origin, because the denominators are defined. This is never 0 now, right? Because I always project onto the circle. And this is my new metric. So there's a shift. The shift is not necessary, but what this metric does is rescale the radius so that you're sort of doing things with respect to a unit circle, right? Makes sense? And you could actually use this metric for the circle case, but you don't need to. So this includes, of course, the standard, the case we've already done. But this was the, as I said, the mildly intelligent beginnings of things, maybe. If we use that metric, and it is a metric you can check, the theorem carries through from before, that you get the scaling factors 1 over the product being the factor in an equality, when you apply the maths, right? We can check with the previous counter example that if I use this new metric, the distance here is 0.028 and it shrinks to 0.005. So at least the counter example is now repaired, right? And you can actually do the proof to, obviously if A1 and A2, if you're outside, these are bigger than 1 and you have a contraction, okay? And again, if they're disjoint, then you're able to say this is strictly less than 1. That's where the circles being disjoint was important early on, and then we were able to remove it later. So I can go through with the same build-up now. Let Ti map Sj to Si. Well, hey, that's contractive with respect to dSi, the circle that things get sent to. Let the union of all the star-shaped sets be X. Nice. Define T bar to be T of I if I'm inside, and the identity, this should be outside, right, not in, and this should be, in Sj, J different from I, so that's cool. And X if I'm in Si, same as before. And now we need a metric that'll work on the union of all of the SIs. And there's a little delicate thinking here, but it's not so bad. The metric on on everything is the SI metric if both points are inside, and otherwise it's the maximum of all the metrics, okay? And this works as a metric, and in particular with this construction, you get contractivity, okay? So now I can take pairwise, because again, I'm thinking non-touching, right? If I take pairwise, I get a contraction with respect to this new metric, right? And it sends things into TI because it's the second map applied, or to SI because it's the second map applied. Everybody's happy, I hope. And following the previous work, we can just take the union of all these pairwise compositions, and this is contractive as long as the stars aren't touching. Then you can let them touch, and you can nudge and take the union as long as they don't all overlap at some point, and you can build the whole framework. It's beautiful. Okay? So here are the pictures. So what I've done in these pictures, this one is all circles, but this one has squares and circles. But initially, the inversion points are the center. So this was already justified under the previous framework. This one not. What I'm going to do now from frame to frame is move the center slightly so that we can watch the fixed points or the attractors change continuously, right?
So you're always using circles though? If you
On the left?
No, not on the left. I'm using squares.
Oh, you're using squares?
Yes,
On the right.
and now that and on this one, yes, I'm using circles, but the inversion point is not at the center anymore, so the circle alone stuff doesn't apply to this construction, right? Only the initial picture. And so you start getting these very interesting shapes, and I apologize that they're not as rich as they could be. The ones on the 2015 paper from Fractals are just glowingly sexy, sorry, it's the best I could do with the troubles that I was having. Oh, I'm going backwards. Cool. You can hybridize now in the circle case. In the circle case, I can take the usual maps for the Sierpinski gasket, contractive in D2, combine it with some circles, with inversion points being the center, contractive in D2, put the whole thing together, and play the chaos game, or there is an attractor, we'll play the chaos game to draw it, and you end up getting these circle inversion remnants cascading through all of the holes of the gasket and so on. It's kind of pretty. My student, Bryson, was fascinated. I had the luck to teach him a topics course where we talked about IFS fractals and various things, and he really liked the local IFSM and the imaging stuff and so on. So he was interested in building a signal representation or function representation framework. So I don't have the detailed explanation of this. I'm assuming people in the room are aware of IFS with gray level maps, that's the M, and the local business. The idea is, if you look at the green lines that are on here, I've sort of lifted them up on the y-axis to make the picture readable. The green lines projected down cover 0, 1. I'm going to define a function on 0, 1, and then take bigger parts of that function, which correspond to the red things shot down. These are the parent domains, and they're twice the length of the child domains. And what Bryson did was take the parents and sort of slide them over some fixed amount. And initially with the child here, you have all these parents to the right, and these are the inversion points for that parent. In other words, if I take a red die and take the diamond at the appropriate height, inverting the red die with respect to that diamond gives me the green guy. So the parent goes onto the child. With me? Okay. As you move up to interior children, now you start to have parents on the left, parents on the right, and all of them can be mapped on. So this is an exhaustive list of parents with the constraint that parents are twice the children, and he's doing some marginal step of the parents as he moves them across. With this construction, you go through and you find which parent maps best to which child in terms of trying to represent the function. I don't think I have to talk about it in detail. Everybody's probably well aware. But I thought it was fun to show the iterations because they're different than what you see with IFS. So first iteration, I have to confess that I didn't constrain to stay in 0, 1, so I have a break here of what shouldn't happen. It would be symmetric if I did that. And slowly but surely, right, we get a fixed point that approximates the signal. And so Bryson wanted to play with that, so I let him. And I finished on time, actually. So,
Thank you.
and I have a thank you.
Any question? So you said you have programs already which are higher resolution plotters as
Yes,
well?
yeah, sure. But we all have our own life-related things, but my father fell 2 weeks ago. So I've been in the hospital a lot in the last 2 weeks visiting, and so I didn't have time to upgrade the pictures as I would have liked to. So I'm sorry for that.
Oh, no, that's
But,
okay. I was just
you know,
wondering.
yeah, the paper will have nicer pictures, which we are writing.
And this is with your student? Or?
Yes. Yeah.
Very nice.
Thank you.